Like electromagnetic radiations which exhibits wave and particle nature, the same way matter also exhibits wave and particle nature. For an electron, it is impossible to measure simultaneously. That means at the same time you won't be able to measure the position as well as momentum. Psi is a wave function, and what actually is of importance is psi square, which gives the probability of finding an electron in a region inside the atom. Hello everyone, this is Ambli Unnikrishan from the Department of Chemistry, Vidhyaashram School of Excellence, Mysore. In the last session, we discussed about the BOHR theory of hydrogen atom and how we could explain the line spectrum of hydrogen with the BOHR theory of hydrogen atom. And yes, we discussed about the factors or the developments which were leading to the quantum mechanical model of atom, which we'll be discussing in detail in this session, right? So in this session, we will be discussing about the dual behavior of matter. That was the first development leading to quantum mechanical model of atom, and then we will be discussing on Heisenberg's uncertainty principle, and then we will study about the quantum mechanical model of atom, and then finally quantum numbers. Clear? So let us begin with the dual behavior of matter. So in previous sessions, we have studied that there is a dual behavior of electromagnetic radiation, right? It behaves as particle as well as wave. So in this session or in this case, we are going to study about the dual behavior of matter. Yes, so in 1924, de Broglie, a scientist named de Broglie, proposed that matter, like radiation, we have studied before, like radiation, also exhibit dual behavior, that is both particle and wave nature. So in 1924, de Broglie was able to conclude that like electromagnetic radiations which exhibits wave and particle nature, the same way matter also exhibits wave and particle nature. So, like photons, electrons also have momentum and wavelength. So, the relation between wavelength and momentum is given by lambda is equal to h by mv, that is equal to h by p. So, what is this? So, based on his experiments that he did on the dual nature or the dual behavior of matter, he was able to calculate or he was able to formulate an equation for the wavelength. Okay, so it is called as de Broglie's wavelength, which is equal to lambda is equal to h by mv. Okay, clear? Now h is, we already know, it is Planck's constant, 6.626 into 10 to the power minus 34 joule second, right? And what is m? M is the mass and v will be the velocity. And we know that mass into velocity is actually momentum, right? So that is what is written here, h by p. Yes, so using this formula which he formulated, the wavelength can be calculated, where m is the mass of the particle and p is the momentum. Clear? Now, let's do a question based on the equation that we studied. Calculate the mass of a photon with wavelength 3.6 angstrom. So, let's see how to calculate this. We know the equation lambda is equal to h by mv. So, what is it that we have to calculate? We have to calculate mass, right? So, m will be equal to h by lambda v. You can just rearrange it, right? So, we know the value of h, that is Planck's constant 6.626 into 10 to the power minus 34 divided by lambda is given 3.6 angstrom. So, what is angstrom? How do I convert angstrom to meter? So, 1 angstrom is 10 to the power minus 10 meter. Clear? So, what do I do? 3.6 into 10 to the power minus 10 should be also added. Then, multiplied by, what is the velocity? We know it is given, calculate the mass of a photon. So, what is the velocity? It is 3 into 10 to the power 8 meter per second. Clear? So, once you calculate, the value obtained is 6.135 into 10 to the power minus 29 kg. So, it is important, it is given in angstrom. So, from angstrom, it should be converted to meters, right? So, that is 3.6 into 10 to the power minus 10. And the velocity is 3 into 10 raised to 8. So, this is clear, as simple as that. Just substitute it to the equation. Clear? So, that is about de Broglie's wavelength. I hope the equation is clear for you. Now, moving on to the second development which led to the quantum mechanical model of atom, which is Heisenberg's uncertainty principle. So as you can see from the name, uncertainty, some uncertainty is there. So let us see what exactly is the principle. So the principle states that it is impossible to determine simultaneously the exact position and exact momentum of an electron. So what does this mean? For an electron, it is impossible to measure simultaneously. That means at the same time, you won't be able to measure the position as well as momentum. Either at a particular time, you may be able to calculate the momentum or else the position. But simultaneously at the same time, both of this can't be calculated. So this is Heisenberg's uncertainty principle. That is, it is impossible to determine simultaneously the exact position and exact momentum of an electron. So he, with the help of an equation, or he formulated an equation to explain this Heisenberg's uncertainty principle. So delta x into delta p is greater than or equal to h by 4 pi. So delta x, what is delta x? We know that x represents position, right? So delta x means it is the change in position multiplied by delta p, that is uncertainty in momentum. It must be greater than or equal to h by 4 pi. Yes? Okay. Now, we know that momentum is mass into velocity, right? So, also it can be written as delta x into, how do I write delta p? M into delta v. Mass will be a constant, right? I need not write delta m. Mass will be a constant. M into delta v, that is uncertainty in velocity, will be greater than or equal to h by 4 pi. Clear? So, that is what is written here. And if you need to take the uncertainty in position and uncertainty in velocity only, then you can bring down the m from here to here. So that is the equation which is written here. So where delta x is the uncertainty in position and delta p is the uncertainty in momentum. So I hope this equation is clear for you. So this is Heisenberg's uncertainty principle. That means at a particular time, simultaneously, you won't be able to measure the exact position and exact momentum of an electron. So what does this actually mean? That simultaneously you can't obtain the values for both of this, position and momentum. So basically that means that it is opposing what Bohr model suggested. That is, electron is revolving around the nucleus in orbitals. So if it is moving in circular paths, that means exact position and exact momentum we can easily calculate. Right. So, according to Heisenberg's principle, it can't be calculated at the same time. That means some problem is there, right? So, what Bohr formulated, according to him, it is in circular paths. But actually, from this principle, it was found out that it is not actually, the electrons are not actually revolving in these circular paths, which we will be discussing in the quantum mechanical model. So, that is about it. Now, let's do a question based on this. A golf ball has a mass of 40 gram and a speed of 45 meter per second. If the speed can be measured with the accuracy of 2%, calculate the uncertainty in position. So, you can see the uncertainty in position we have to calculate. So, suddenly that thing should come to your mind. Okay, we have to use this equation, right? So, which is the equation that we studied according to Heisenberg's uncertainty? That is delta x into delta p is equal to h by 4 pi. Right. Yeah. So what is given? A golf ball has a mass of 40 gram. Mass is given. So you can write it in this form, delta x into m delta v is equal to h by 4 pi. Okay, mass is given, speed is also given. There is one more sentence. If the speed can be measured with the accuracy of 2%. So that means we can calculate the uncertainty in velocity. How it is calculated? It is given 2% accuracy. That means 2 by 100. It is given in percentage. No? So 2 by 100 into 45. 45 meter per second. So that gives you 0.9 meter per second. So that will be your uncertainty in velocity. Now we know uncertainty in velocity here. Mass also is given. What do you have to calculate? Uncertainty in position, right? So how can I rearrange the equation? Delta x will be equal to h by 4 pi m into delta v. So let's substitute the equation. What is h value? 6.626 into 10 to the power minus 34 divided by 4 into pi value is 3.14 multiplied by what is m? Mass is 40 gram. 40 gram, how do you convert it to kilogram? 10 to the power minus 3, right? So it is 40 into 10 to the power minus 3. It must be represented in kilogram, right? Multiplied by the delta V, what did we calculated? The uncertainty in velocity is 0.9. Clear? So from that, what is the final answer that we get? So what is the delta x or uncertainty in position? It is delta x is equal to, once you calculate this, you will get 1.46 into 10 to the power minus 33 meter. Yes. So this is how you calculate it. I hope it is clear. Now moving on to the significance of uncertainty principle. So what exactly does it say, or what from this Heisenberg's uncertainty principle, what is that we can obtain? Yes, it rules out the existence of definite paths or trajectories of electrons, right? So that is what I was talking about when we were discussing about Heisenberg's uncertainty principle. So if we are not able to exactly calculate the momentum and position at the same time, that means it rules out the existence of this definite paths or trajectories that was discussed in Bohr's model of atom. So that means actually it won't be revolving around the nucleus in orbits, right? Circular paths. And Heisenberg's uncertainty principle is significant only for motion of microscopic objects and negligible for macroscopic objects. So we won't be able to use the Heisenberg's uncertainty principle in case of macroscopic objects. It is only applicable for microscopic objects. So these are the two significance of uncertainty principle. First one, it rules out the existence of this circular paths or trajectories in which the electrons are revolving around the nucleus, right? And also it is only applicable for microscopic objects and it is negligible for macroscopic objects. Now, from this Heisenberg's uncertainty principle and the dual nature of matter, it gave certain limitations to Bohr model of atom. So why exactly this Bohr model of atom was being thrown out? It is because the wave character is not considered in Bohr model. Yes, we studied that matter has dual nature. It behaves as wave as well as particle. So this wave nature was not considered in Bohr model. That was one limitation. Now, according to Bohr model, electrons are present in orbits which is not possible according to Heisenberg's uncertainty principle. That is what we discussed just now. These are the few limitations that caused the Bohr model of atom to fail. Clear? And from this, the quantum mechanical model came into existence. Okay? Yes. Now let's discuss about the quantum mechanical model. So what exactly is quantum mechanics before that? So quantum mechanics deals with the study of motion of microscopic objects that have both wave and particle nature. So in quantum mechanics, we study about microscopic objects, right, which has both dual nature, that is particle as well as wave nature. Now, quantum mechanics was actually developed independently by two scientists, that is Werner Heisenberg and Erwin Schrödinger in the year 1926. Now, let's discuss about few important features that you have to remember under quantum mechanical model of atom. Okay. So, the first one is energy of electrons in an atom is quantized. Okay. So, energy of the electrons in each atom, the energy of electrons is quantized. That means it is having a particular value. Clear? Now, path of an electron can never be determined accurately. As we studied in Heisenberg's uncertainty principle, the path, in which path this electron is moving, it is certainly not a circular path or orbit. Yes, it can't be determined perfectly or accurately. Clear? Now, next one, an atomic orbital has wave function psi and there are many orbitals in an atom. So, what is this orbital or what is wave function and what is atomic orbitals we will be studying. Okay. So, what you have to understand is in an atomic orbital has wave function psi. So, what you have to understand is psi is basically a function which is used to represent the atomic orbitals. Okay. And there are many orbitals inside an atom. In an atom, there are, it's just not one orbital, many orbitals are present. Clear? Yes. Now, an orbital cannot have more than 2 electrons. In each orbital, there can be only a maximum of 2 electrons. And orbitals are filled in increasing order of their energy. This way, this in detail we'll study in the upcoming session. and all information about electron is stored in orbital wave function psi. So psi is basically a wave function which is used to, yes, it is basically a wave function which gives the information about the electron which is present in it. And the probability of finding an electron at a point within an atom is proportional to the square of psi. So as I said, psi is a wave function, and what actually is of importance is psi square, which gives the probability of finding an electron in a region inside the atom. Okay, and from the value of psi square, it is possible to predict the region around the nucleus where the electron is most probably found. So from this, what you can understand, yes, it is the electrons are not moving around the nucleus in exact circular paths. So there are certain regions in which the probability of finding electron is more, which is given by psi square. So what exactly is atomic orbital? It is basically the region in which the probability of finding an electron is high. Okay, so to understand more about the orbitals, the atomic orbitals, where exactly is present, the shape, the size, the orientation of it, you need to study about what is called as quantum numbers, which will help you in correctly defining and understanding the details about the atomic orbitals. So I hope this part is clear. So before moving on to the quantum numbers, you need to keep this in mind, which is of importance. That is, the electrons are present inside the orbitals that we already understood from the informations that were given regarding the quantum mechanical model of atom. So what did we discuss till now? There is a positively charged nucleus. There are different energy levels, right? So each of these energy levels are called as shells, okay, which is represented by 1, 2, 3 K element that we have studied. So inside these shells, there will be subshells that are present. We will be studying what exactly this is in the next slides, okay. So in shells, there will be subshells, and corresponding to each subshells, there will be orbitals, okay. So certain subshells will have certain number of orbitals. So this is a basic thing that you have to understand. See, these excited states or these stationary states that you can see, they are called as shells, in which subshells are present. Each shell contains different number of subshells, and each of the subshells corresponding to it, different number of orbitals will be present, inside which electrons are present. Clear? Yes. So now moving on to quantum numbers. So what exactly is quantum numbers? Atomic orbitals can be specified by giving their corresponding energies and angular momentums, which are quantized. So these are used to get complete information about the electron, their location, energy, spin, etc. So using this quantum numbers, we will get to know more about, or we will be able to gather the information about the atomic orbitals. Also, we'll be able to understand the location, energy, spin, etc. about the electron. So basically, you have to study about 4 quantum numbers, which is very important. The first one is principal quantum number. Yes, this might be familiar for you. We have discussed regarding this in previous sessions. I said at that time we will be discussing it in detail here, right? So that is principal quantum number. Second one is azimuthal quantum number, represented by small l. Magnetic quantum number represented by m, or it can also be represented by ml, l in the subscript form. Spin quantum number, which is represented by the letter small s, you can also represent it as ms. Clear? So let's begin with the first one, that is principal quantum number. So what is principal quantum number represented by the letter small n? It represents the shell to which the electron presents. Okay. It gives us which shell is the electron present in. So we studied, right? There is a positively charged nucleus. There are different energy levels, and each of these are called as shells. Right. So the shell, to which shell this electron is present, or in which shell this electron is present, that will be given using the principal quantum number. So if n value is 2, that means the electron is present in the second shell. Right. So we can represent the shell to which the electron is present based on the principal quantum number. It gives the size and energy of the orbital as well. Okay, the size and energy of the orbital. So n is equal to 1, 2, 3, 4. That is how you represent it, or else you can also represent it as KLMN. Right. And it also tells about the number of orbitals in a given shell. Okay, so we know that if n is equal to 1, that means the electron is present in the first shell. So it also, if we know the n value, you will be also able to calculate the number of orbitals in that shell. So how do we calculate? That is using n square. Okay, so in the first shell, there will be only one orbital. So if it is n is equal to 2, that means the number of orbitals, how do you calculate? If I know the principal quantum number, it will be 2 square. That will give you 4. There will be 4 orbitals. Clear? Now that is about number of orbitals in a shell. If n is known, we can calculate the number of orbitals, right? And also the maximum number of electrons in a shell can also be calculated using the equation 2n square. We know that n square represents the number of orbitals in a shell. So it's simple. We have to multiply n square by 2. So why this 2? So when we were discussing about the details of quantum mechanical model, I hope you remember we studied that in an orbital, only 2 electrons are present. So if the number of orbitals in a shell, it's n square, that means number of electrons will be multiplied by 2, right? So that is 2n square. Clear? Yes. So I hope you understood. So if the shell is K, that means the principal quantum number, the n is given as 1. Right? And the number of orbitals, how do you calculate? N square. So 1 square is 1 and the maximum number of electrons is multiplied by 2, 2n square, which gives you 2. Clear? Yes. So in an orbital, only 2 electrons are present. So as in the first shell, only one orbital is present. It has 2 electrons. Clear? So coming on to L shell. L shell is represented by n is equal to 2, where the number of orbitals will be 4, right? N square. So what will be the number of electrons multiplied by 2, which will give you 8 electrons. Now moving on to M shell, n is equal to 3, number of orbitals will be n square, that is 9, and maximum number of electrons will be 2 into n square, that is 9 into 2 will give you 18 electrons. So like this way, you will be able to define for K, L, M, N shell, right? So n is equal to 1, 2, 3, 4. Corresponding to that, you will get the n values. So this is about principal quantum number, where you will be able to calculate the number of orbitals and the total number of electrons which is present. Clear? So it what and all information you can get? It represents the shell and it gives the size and energy of the orbital. So I hope it is clear. So moving on to the next one, that is azimuthal quantum number, which is represented by the letter small l. Okay, principal quantum number is small n, azimuthal quantum number is small l. So it defines the 3-dimensional shape of orbital. So it gives the 3-dimensional shape of orbital. How exactly is the 3D shape of the orbital will be provided by azimuthal quantum number, and it gives the number of subshells present in a main shell. So when you calculate the L value, that is actually equal to the number of subshells which is present inside a shell. Clear? N value gives that is the principal quantum number, tells you the shell, and L value, that is azimuthal quantum number, tells about the subshell, number of subshells which is present inside a shell, and it gives the shape of the orbital. Yes, and number of subshells will be equal to n, and L can have values ranging from 0 to n minus 1. So what does this mean? So let us say, if my principal quantum number is 1, that means L value can be 0 to n minus 1. L can have values which is ranging from 0 to n minus 1. So in this case, we know n is equal to 1. That means 1 minus 1 is 0. So 0 to 0, what does that mean? Only 0, right? So L can have only value that is 0. So L is equal to 0, as you can see in that table. L is equal to 0 corresponds to which subshell? It will be S subshell. Okay. So L is equal to 0 value corresponds to, or else the notation for the subshell is S. You can say that it consists of only one subshell, that is S subshell. Clear? So let us take one more example. When it is n is equal to 2, we know the principal quantum number, that is n is equal to 2. So how do you calculate L? L can have values which is ranging from 0 to n minus 1, right? So 0 to, what is n minus 1? 2 minus 1. So it can have values from 0 to 1, right? So L can have two values, that is 0 and 1. That means when the principal quantum number is 2, that is the shell, which is the second shell, can have two subshells, 0 and 1, right? So that means two subshells. So it is having an S subshell as well as a P subshell. Clear? So when the L value is 0, it corresponds to S, 1, P, 2, D and 3, F. Yes, so I hope that is clear. Now let's quickly fill this table so you will understand it in a better way. Okay, so let's take the principal quantum number to be 1. Yes, what is the shell? 1 corresponds to K shell, right? Yes, it is K shell. Now, how many or the number of subshells? If the N value is known, what is the number of subshells? Yes, the number of subshells is also equal to N. That will be 1. Right. Now, what is the L value? L value, we know that it ranges from 0 to N minus 1. That is 0 to 0 only. Right. In this case, N minus 1 is also 0. So, that means 0. Now, that means what is the subshell? Which subshell is present? S subshell is present. Clear? Only one. That is S. Now, moving on to the next one. N is equal to 2. Okay. So, what is the shell? Notation, it will be L shell, right? Now, number of subshells, we know that if N is equal to 2, number of subshells is also equal to N, right? So, you will have 2 subshells in this case. So, what are the values of L here? Which are the 2? Yes, L is, we know that it ranges from 0 to N minus 1. N is 2 here, 2 minus 1 is 1. That means 0 to 1. So, 2 values, 0 and 1. So, as you can see, 0 corresponds to S and 1 corresponds to P. So, there are 2 subshells S and P in this case. Now, moving on to N is equal to 3. K, L, M, right? It is M shell. Okay. N value is 3 means number of subshells will be also equal to 3. So, we know that L value ranges from 0 to N minus 1. That is 0 to 3 minus 1. That is 2. So, ranges from 0 to 2. That means 0, 1, 2. 3 values are there. So, corresponds to 0, S orbital is there. Sorry, S subshell is there. P subshell is there and D subshell is there. 2 corresponds to D, right? Now, moving on to 4. N is equal to 4. N shell, right? And number of subshells is also 4, right? Yes. And L value can range from 0, 1, 2 and 3. That means subshells can be S, P, D and F. So, I hope it is clear. So, this all round gives you a basic idea about the azimuthal quantum number. So, I hope it is clear. Now, moving on to the third one, that is magnetic quantum number or magnetic orbital quantum number, which is represented by ML or M. You can either represent in either way. This small letter M or ML, subscript L. Okay. Now, it gives the information regarding the spatial orientation of the orbital with respect to standard set of coordinate axis. So, it gives you spatial orientation of the orbital in space. Yes, in 3D space, how the spatial orientation of the orbital will be given by the magnetic quantum number. Okay. Now, it determines the number of orientations of electrons present in a subshell. It gives the number of orientation, in which all orientations the electrons can be present, is given by this. And it gives the number of orbitals in a subshell. Yes. So, using azimuthal quantum number, we were able to calculate the number of subshells. Now, using magnetic quantum number, we will be able to calculate the number of orbitals if we know the subshell. Clear? So, basically, it can have values which is ranging from minus L to plus L. Yes, we know how to calculate L value, that is 0 to N minus 1. Once we find L value, minus L to plus L, ranging from minus L to plus L, ML values will be there. That is magnetic quantum number. So, number of possible values of magnetic quantum number, that is total number of orbitals which will be present is 2L plus 1. So, let us fill this table and try to understand it much more clearly. Now, value of L, let me say the value of L is 0. Okay. So, the subshell notation is S, right? We know that for 0, the subshell is S subshell. Now, what will be the total number of orbitals which is present? That is 2L plus 1, right? So, L value, we know that it is 0. That means 2 into 0 is 0 plus 1, only 1 orbital. Clear? So, what we can conclude from this? We know the subshell. So, S subshell consists of only 1 orbital. Clear? Now, moving on to value of L is equal to 1. 1 means the subshell notation is P. P subshell. So, that is P subshell, right? So, the number of orbitals is 2 into, what is P? 1, right? The value of P, 1 plus 1. So, that will give you 3. That means, in P subshell, there are 3 orbitals which is present. Clear? Now, moving on to 2. When L is equal to 2, that is D, right? D subshell. Inside D subshell, 2 into 2 plus 1, there will be total of 5 orbitals. Clear? S subshell has only 1 orbital. P subshell has 3 orbitals. D subshell has 5 orbitals. Now, what about F subshell? 2 into 3 plus 1 will give you 7. There will be a total of 7 orbitals which is present. Right? So, we started from shell, inside which subshells is present, and corresponding to each of the subshell, we understood how many number of orbitals will be there. Right? For S, it is 1. For P subshell, 3 orbitals will be present, D 5 and F 7. Yes, so I hope magnetic quantum number is clear. Now moving on to the last one, which is spin quantum number. It refers to the orientation of spin of the electron. It gives us the idea about spin of the electron, in which direction the electron is spinning. So basically it can have only two values, that is either plus half or minus half. Earlier we discussed that in an orbital, maximum of 2 electrons can only be present. So what you have to understand is, in that 2 electrons, one will have a plus half rotation and one will have a minus half rotation. So plus half rotation means it is rotating in clockwise direction. Minus half corresponds to anti-clockwise direction. So this is how you can represent it. This is one electron and this is another electron. Yes, which will be spinning in opposite direction. Right? So that is about spin quantum number. So I hope till here what and all we have discussed, the 4 quantum numbers are clear for you. Principal quantum number, azimuthal quantum number, magnetic quantum number and spin quantum number. I hope it is clear, right? Yes. So I hope you are also clear with the shell, subshell and the orbitals concept. Yes. Now let's do few numericals based on this. Okay. Now, first one, what is the total number of orbitals associated with the principal quantum number n is equal to 3? So, principal quantum number is given as 3. So, we know that if the principal quantum number is given, we know the principal quantum number, we can calculate the total number of orbitals which is present in that shell. Which equation? N square, right? N square will give you the total number of orbitals which is present. That is 3 square, which is 9. Yes, this is the total number of electrons. So if the question asks you also to find the total number of electrons, how can you find it? It is 2n square, right? That is 9 into 2, 18 electrons will be present, right? I hope it is clear. Yes. Now moving on to the next one. How many number of electrons in an atom may have the following quantum numbers? Okay. So how many number of electrons? You have to calculate the number of electrons that can have this possible quantum number. The quantum numbers are given. The principal quantum number and spin quantum number is given. You have to calculate how many electrons can have this possible set of quantum numbers. So principal quantum number is 4. It is given. Okay. And spin quantum number is given as minus 1 by 2. Okay. So principal quantum number is given as 4. So, from that we can calculate the total number of electrons, right? Like in this way we can calculate the total number of electrons. So, n is equal to 4 means the total number of electrons which can be present is 2 into n square, that is 2 into 16, a total of 32 electrons can be present. Yes, in this n is equal to 4 shell, a total of 32 electrons can be present. Now, one more part is there. The spin is minus half. So, when we were discussing about spin quantum number, I told in an orbital, one will be having plus spin, that is plus half, other will be having minus half. If a total of 32 electrons are present, that means out of which 16 will have plus half rotation, right? And the other 16 will have minus half rotation, right? So, in a total of 32 electrons, 16 will have plus half rotation and 16 will have minus half rotation, right? You remember, we represented it like this, right? This is for plus and this is for minus. So, half of it will have plus rotation, half of it will have minus rotation, right? So, what is the answer for this? There will be 16 electrons that can have this possible set of quantum number. I hope it is clear. Now, moving on to the third one, n is equal to 3. Principal quantum number is given as 3 and the azimuthal quantum number is given as 2. Okay, so how many electrons are possible if this is the quantum number that is given? This is the set of quantum numbers. So, n is equal to 3 and L is equal to 0. L is equal to 0 means how many magnetic quantum number values are possible, ml values are present. It ranges from minus L to plus L, right? So only 0 is there, that means ml will be also 0, right? So only one orbital is present, inside which we know that either it can have plus half or minus half rotation, right? So how many set of electrons can have this set of quantum numbers? It will be 2, right? Yes, clear? So either it can have plus half rotation or minus half rotation. What do we have to calculate? Number of electrons that can have this set of quantum numbers. So that will be 2. So I hope this is clear. Now one more question. Which of the following set of quantum numbers are not possible? So in here a set of different set of quantum numbers are given. You have to see which all are not possible. Okay, let's see. First one, n is equal to 0, L is equal to 0, ml is equal to 0, ms is equal to plus half. See, n is principal quantum number, L is azimuthal quantum number, ml is magnetic quantum number and ms is spin quantum number. We know that. Now first one is n is equal to 0. Yes, is n is equal to 0 possible? No, right? The n value starts from 1, right? The principal quantum number value starts from 1, 2, 3, etc. Right? Yes. So that is of course not possible. You need not go into the other values. Right? Now the second one, n is equal to 1. Okay. L is equal to 0. L is equal to 0. Is it correct? N is equal to 1 means what L values can it have? 0 to n minus 1. That is only 0 is possible. If L is equal to 0, what will be ml value? Ml value will be minus L to plus L. So that is also 0. And ms can be either positive or negative 1 by 2. Clear? So this is possible, right? This is possible. This is not, the first one was not possible. Now the third one, n is equal to 1. Okay, that is okay. Now L is equal to 1. Is it possible? If n value is 1, L value 1, is it possible? We know that if n is equal to 1, how do you calculate L? It ranges from 0 to n minus 1. N minus 1 is 0. N minus 1 means 1 minus 1 is 0. So L can have only one value, that is 0. So is this possible? L is equal to 1 is possible? No, right? So yes, this is also a not possible set of quantum number. Now moving on to the fourth one, n is equal to 2. L is equal to 1. If n is equal to 2, we know that L value ranges from 0 to n minus 1. That is 0 and 1. Two values are possible. ml is 0. We know that ml ranges from minus L to plus L. Yes, so it can have minus 1, 0, 1 value. So that is also not a problem. ml is equal to 0. And ms, spin quantum number, can be minus half or plus half. So this is also possible. Now moving on to third one, n is equal to 3 and L is equal to 3. So now moving on to the fifth one, n is equal to 3 and L is equal to 3. Of course, this is not possible, right? If n is equal to 3 means L value must be of course 1 less than that. That is 0 to n minus 1, right? So it can have values 0, 1 and 2, not 3, right? So this is not possible. And the last one, n is equal to 3, L is equal to 1. N is equal to 3. Okay, so L can have values 0, 1 and 2, right? And ML value is 0. Yes, ML can have values minus 1, minus 2, 0, 1, 2, right? Yes, so MS is plus half. So this is also possible. So what did the question ask you to find? The quantum numbers that are not possible. So A is not possible, C is not possible, E is also not possible. So from these examples and the details that we have studied till now, I hope the quantum numbers is clear, and the concept of shell, subshells and orbitals and how you can calculate the number of each of it is clear, I hope. So that's for today's session. So in the next session, we will be studying about shape of the orbitals. We studied about shells, subshells and orbitals today, right? We will be studying in detail about the shape of each of these orbitals, clear? And then energies of these orbitals. And there are 3 principles or laws which you have to study, which is very, very important. Aufbau principle, Pauli's exclusion principle and Hund's rule of maximum multiplicity. And finally, the electronic configuration of atoms, from which we will end this chapter. Okay, so that is about next session. So I hope what and all we have discussed in this session is clear for you. So that's all for today. Thank you.